So we were saying, what if I use now 3 segments? So if I use 3 segments, the length of each segment will be 0.8 over 3, which is equal to 2.667. And then I will have x0, I will need 4 points. x0 is 0, x4, x3 is 0.8, x1 will be 2.667, and x2 will be equal to 2 times 2.667. Okay, and then I will just replace in my formula. So I compute, I have the function f, I can find f of x1, I can find f of x2. Already f of x0 and f of x3, which are 0 and 0.8, are computed before. So all I have to do is to replace, and I put instead of n3, I get that the relative true error is 16.5%. So now it decreased also very well from 35 to 16.5 by going from 2 to 3. So as you can see, I can decrease largely the error by increasing the number of segments. So let us use now 4-segment trapezoidal rule. For n equals to 4, I will get the following. I have 5 points now, x0, x1, x2, x3, and x4. And to determine what are these axes, so x0 is 0, of course, the last one is 0.8. Now to know what is the length of each segment, I say it's 0.8, the initial width of the segment, the big segment, over the number of segments I'm doing, which is 4, which is equal to 0.2. So then x1 will be 0.2, x2 will be 0.4, and x3 will be 0.6. And now all I have to do is to apply the general formula of integration and get the value of integral estimated. And as you can see, I was able to reduce the true error to, it was initially 90% when I took one segment. When I took now 4 segments, it is 9.5%. But as you can see, the disadvantage of trapezoidal rule is that I might to take several segments to reach a good error. So if I want to have a high accuracy, let's say I want to have an error below 1.8%, then I should take 10 segments, which will take a lot of time. This is why we will come up with more efficient rules to calculate the integration. Okay. Now you can compare here how the error is decreasing, and you can see that it's nearly, so we know that it's proportional to n squared. So we expect that when we go from 2 to 4, it's nearly divided by 4, because here n squared is 4, here n squared is 16. So when you divide, because you are dividing by n squared, then you expect your errors to be divided by 4 nearly. So here it's nearly 40, here it's nearly 10. Why I say it's approximately, not exactly divided by 4? Who can tell me? Why it's not exactly?
لأنه في الاف دبل برايم ما عم نعرف قد ايه.
Very good. هيدي الاف سكند بار بتتغير مع النمبر اوف segments، لانه هي كل مره بتاخذ الافريج اوف اف سكند at the different points، وهذا كل ما زاد النمبر اوف segments حتتغير هيدي الفاليو، لانه حاخذ segments جداد وحيكون الفاليو اوف اف second somewhere in these intervals، ما بعرف وين. So when I do the average، اذا عندي 3 segments مش مثل ما يكون عندي 4، ما حيطلع نفس الافريج. This is why this will change, and we don't know by which amount. This is why we say approximately. يعني the order of change is nearly proportional to n squared, but مش exactly لأنه في كمان هيدا الفactors that will affect. Okay, and here from 4 to 8 you have كمان approximately it's divided. The n is times 2, error is divided nearly by 4 from 10 to 2.5 nearly. Okay, so it is good to increase the number of segments, but also it will take more computational time. This is why we need to come up with, for highly nonlinear functions, we need to come up with new methods, and this is what we will introduce now. So in comparison with the trapezoidal rule, which perform linear interpolation between points, we will introduce the Simpson's 1/3 rule, which perform quadratic interpolation. So the first difference is that here we need, for one segment, we need just 2 points to do linear interpolation. However, in Simpson's 1/3 rule, for each segment we consider, we need 3 points. Okay, 1, 2, 3, and we take the second point just at the middle between these 2 points. And we can define then h, which is the distance between the first and the second point, and the distance between the second and the third point, as b minus a over 2. And now we will interpolate the function that we have by a quadratic function. This is why for highly nonlinear functions, Simpsons will work better than trapezoidal rule, because here you have a linear behavior, which is very far from, let's say, curve that we have. While when we have a quadratic function has curvature, so it can compute better the case where we have very nonlinear curves. So let us see how to define the Simpson rule. It is very simple. Now, the first thing to say is that I want to interpolate, I want to find an interpolating function passing by the data points. Okay, so I need to do or Newton interpolation, or here what they did, which type of interpolation they used.
Lagrange.
Yes, exactly. Okay, they use Lagrange interpolation. So this is L1, or you can call it here, you can call it L0 because it's for x0. This is L1 for x1, and this is L2 for x2. Okay. And now you can say that I will represent the area under the quadratic curve. I can approximate the integral by the area under the quadratic curve, which can be obtained by just integrating this interpolation function. So if I perform the interpolation function and I replace the boundaries, okay, so just you have to integrate here between a and b. It seems complex, but it's you will end up with integral of a second degree equation, which is very simple to do. So you can find that the general rule will be the following. The integral will be equal to b minus a, which is the width of the interval I considered, times fx0 plus 4fx1 plus fx2 over 6. So as you can see, this method gives a high weight for the middle point, and this will take into account curvatures. This is why it will give better results than linear interpolation. So here, in a similar way to trapezoidal method, you have the width times a certain estimation of the mean function value. But here, you are not taking the normal average. You are taking a certain mean with higher weight for the middle point. And this will help you to follow curvature in a better way, and will give you a good prediction. So if you replace now b minus a by its value, because you know that b minus a can be replaced by 2h, okay, is equal to 2h. If you replace b minus a by 2h and you simplify 2 over 6 is 1 over 3, we'll end up with the following general formulation for Simpson's rule, which is Simpson's 1/3 rule, which is h over 3 times fx0 plus 4fx1 plus fx2. And we call it Simpson's 1/3 rule because of this coefficient here, 1 over 3. So we divide h by 3. Okay, so we will see that this method represents a very high advantage. And we will see this by seeing the equation of the error. The equation of the error for the Simpson's 1/3 rule is the true error is minus 1 over 90 h to the power 5 times f to the power 4 psi. So here the order of derivative is fourth order, not 3. In general, we expect if we are using a second order interpolating function that the error will be 0 in case the error should be proportional to f-third, because if f-third is 0, then we expect a 0 error. But here, no, it was shown mathematically that it's proportional to the fourth order derivative, so it's even more accurate. So it gives us one order more of accuracy. This is why we say that Simpson's method is very efficient. Okay, and here we can, in this slide, we can see this. They are telling us that since we are using a quadratic function, we expect the error to be proportional to a third, because when